we're looking at circular motion. That's where we're up to in mechanics, okay? Now, you were doing some circular motion just now, right? You had your person in the middle, right? And everyone else moving around them in a circle, okay? I hope you found it interesting. There are a few different things that we can notice, okay? Firstly, let's go back to the beginning. At the beginning, there was just a couple of you, right? There was just a couple of you. And I think, what was our record speed? I think it was like 1.16 seconds. Okay, now, we're all interested in who can win and how fast you can go and, you know, how not wiggly you can make your line and so on, okay? But we have all of this language to describe, like we're more than just fast and slow. We can say, look, see, 1.16 seconds, your first scenario, okay? I didn't make you do a measurement of how far, like, you know, how far you actually walked, but we have a precise measurement for how far that person on the outside went if you just think in terms of an angle. Right? An angle. How far was the angle that that person traveled through? The outside person on the left. How far did they go in whatever time? As an angle, they went 360 degrees. Or, you know, come on, we're in calculus land here, so we're going to go radians. That's 2 pi radians. Okay? So it's about 6.28, roughly. Okay? So because now we have a displacement, it's not like it's not a length displacement, it's an angle displacement, but that's okay. We have displacement, and we have a time, right? So if we have an angular displacement and a time, that means we can work out an angular speed, can't we? How fast someone is rotating. So for example, if we call this angle, oh, that's spelled wrong, sorry, let's try again. If we call this angular displacement, because that's how far they went in total. Angular displacement equals 2 pi radians, okay? I'm just putting in 6.28 so we can get some numbers in our head, okay? Well, therefore, what's the angular speed? Angular speed. What angle has it gone through? Well, I guess you'd divide, and I don't have my calculator out, but maybe you do. It'd be close to 6, wouldn't it? Maybe a bit under 6. What do we get? You can do it exactly. 2 pi divided by 1.16. There we go, 5.4. Roughly 5.4 radians per second. Okay? So, we have this language here of displacement and speed that we're comfortable with, but we're just applying it to angles. No big deal, okay? Now, because it's displacement and speed, that's what we're familiar with, but it's not the displacement and speed or velocity that we're used to. It's all about angles. So therefore, you know, if you call this, say, well, it's an angle, what do we usually call angles? Something like theta, okay? This here, this would be, well, it's change in theta with respect to time. Right? So this is d theta on dt, right? But of course, we already have a convention established for how to talk about these kinds of things. When you're differentiating with respect to time, because that's such a frequent thing, you know when we're talking about just straight line motion, instead of saying x and v and a, you could call it x and x dot and x double dot. That dot means, it means more than a dash, it means with respect to time, okay? So this is theta dot, okay? Same kind of notation, just applied angles. Right, now let me extend this a little more. This idea of angular motion, right? It's so important and it comes up so frequently, and I don't like dots, that we call it its own special thing. Its own special letter. One we haven't used for a while. We call it omega. Okay, that's a lowercase omega, not to be confused with an uppercase omega, which is ohms, I think, electricity, that kind of thing. So this omega, this is what's talking about angular speed. It's just another notation. You can call it theta dot, or you can call it d theta on dt. They're all the same thing. Okay, now, just to push on it a little more, just to have the picture complete for us, we have displacement, we have speed, velocity, okay? What would round out the picture? What's left? acceleration, right? And we can use the same kinds of logic. I can find my blue marker. The same kinds of logic that we had in straight line motion or in projectile to say, well, how would we express this? Okay, so if we talk about displacement, speed, velocity, and acceleration, you can say it a whole bunch of different ways. That's what happens when you get to acceleration. We've noticed this already when we're looking at our introductory exercises in mechanics. We could just say it's this speed, this velocity, differentiated with respect to time, again. So you could call it d omega on dt. Okay, it's just, I mean, we're used to saying it's dv dt, but we don't want to confuse v with this velocity, okay? You can write it a whole bunch of different ways. Obviously, since it's the first derivative of this, that makes it the second derivative of this, right? So you could equally write it d squared theta on dt squared. Okay, think with me, there's a few other ways we know to write acceleration. It's just the same kind of thing, just with different labels. Give me another example. Theta double dot, yep, you'll see that just as many times. Okay, another one, you can give me another two. We have 5 ways of writing acceleration, right? W dot. Okay, yeah, I suppose so. That's true. It doesn't come up much though. I don't know why, but I almost never see that. Think about ways we expressed acceleration before that were useful to us in those like F equals ma type questions. What other ways could we write it? Yeah, good. You can go from here, right? And you can say, well, I can write this as omega d, hold on, I've got it written here. d omega on d theta. Remember how we do that? With chain rule? Because omega, right, that's just d theta on dt. So if I put d theta on dt here, you see it cancels and it gives you back this line, okay? And there's one more way to write it. Instead of half v squared, it'll be half omega squared, right? So you'd say d on d theta half omega squared. It's all the same. It's all the same. It's just omegas instead of v's, and it's just thetas instead of x's, right? Because you've got theta representing angular displacement, okay? So you've got this idea. This is all about angular motion. Okay, so let's do a quick thought experiment here, right? Let's think of our group of 4 people, and they're all going around, okay? Now, what was the time, what kind of times did we get for 4 people? It was like 3 seconds? 2.3, roughly 3 seconds, okay? So think about this person, the second person along, right? How long did it take for them to go all the way around and back to the original spot? It's 3 seconds, right? What about this third person? How long did it take for them to go all the way and then back to their original spot? Also 3 seconds. They all take the same amount of journey. That's why everyone's shoulders were together, in theory, anyway, okay? But hold on a second. You've all gone through the same angle, and you've all taken the same time, 1.16, 3 seconds, 8 seconds, whatever it was. So your angular motion is the same, but the motion isn't the same, right? Get the person on the outside to tell you the motion is definitely not the same. What's the person on the outside doing? They're running. They're moving way faster than everyone else. That lazy guy in the middle, he's not going anywhere, right? It's I know who positioned themselves to be in the middle, okay? So therefore, there's not just angular motion. Angular motion doesn't tell the whole story, right? There's also, now this has a couple of different names. I think the most helpful name is linear motion, okay? Because we're not just thinking about this angle in here, right? So if I were to put an axis here, this angle of 2 pi radians, okay? We're also thinking about a line on which they're moving, okay? So that is, this kind of thing, like a line like that, okay? And obviously, the further you are away from the center, the faster that motion is going to be, okay? Now, how can we express this algebraically? Let's think about, just like this, let's think about speed, okay? So if I talk about, linear velocity. Okay, velocity is distance over time, right? Distance over time. this distance, right, it was an angle, okay? What about this distance? Where is it? It's not in a straight line, right? So how do you measure it? It's a circumference, right? And because we're talking in radians, we can use radian measure language to express this. This thing is not just a circumference, it's an arc, right? It's an arc, okay? So I'm going to have the change in the arc length, right? So it's not straight, and its distance over time. Okay. But we know how to calculate arc length, right? Obviously you need two things. You're going to need the angle, and what was the other thing that you needed to work out arc length? You need the radius, right? So I'm going to say, well, that's d of r theta, that's arc length, over dt, okay? Now keep in mind, we're just thinking about circular motion, right? Circular motion. So that means the radius is the same all the way around. So this r, right? This is a bit confusing, but I think you guys can handle it. This r is a constant. Okay, r is a constant. So therefore, I can just pull it out, right? I can just take that out. So this is going to be equal to r outside of d theta on dt, right? Hold on. We know what d theta on dt is. We gave that a whole name. We called it omega. And of course this makes sense, right? What's r? That's how far you are from the center. The further you are from the center, right, this thing's constant, but it's bigger, right? So therefore, your whole speed is moving faster. This poor guy is running his little heart out, okay? So, that's the picture. These are the equations. You've got two different kinds of motion. You've got angular motion and you've got linear motion, okay? Now, I told you this had a couple of different names. The other kind of name that it has, and you can maybe imagine why this is, in some textbooks it's called tangential motion. Why do you think they call it that? Yeah, it's if you were to illustrate it here, right? When we talk about velocity, velocity is a derivative, right? So it tells you kind of like gradient at a particular point, and it tells you the gradient of a tangent, right? So if I were to represent the velocity there at that particular point, it looked like the tangent going off in that direction, and I guess we'd draw it longer depending on how fast it's going.